Okay, now in this last part of section 2, we're going to discuss the trigonometric ratios of angles that are not acute. Now, you'd know that the acute angles are in fact the ones that fall in the first quadrant. That is, of course, if you were to be moving in the positive sense. Now, if I had an angle in quadrant 1, or in fact, if I had angles in quadrants 2, 3, and 4, how could I basically determine them using their corresponding angle in the first quadrant? For example, here, if you were to look at this unit circle here, in quadrant 1, I have an angle of theta. Now, this is an angle of theta. Now, if this is angle theta in the positive sense, then in quadrant 4, you would have this as angle negative theta in the negative sense. So, since theta and negative theta has the same, in fact, measure for the angle, except one is positive and the other one is negative, then these two would actually be symmetrical. Their corresponding angles or their corresponding segments are symmetrical with respect to the x-axis. So if this is a point of coordinates xy, that is a point with the same x but an opposite y. Similarly, by symmetry, if we'd consider this symmetry of this point with respect to the y-axis, if this is a point of coordinates xy, that would be the point of coordinates negative xy. And these angles would in fact be equal. This angle with that angle, which leads me with this angle being 180 minus theta, or pi minus theta, since this angle and that angle are equal by symmetry. So over here, this point negative xy would actually be forming an angle of 180 minus pi. Okay, and similarly for the third quadrant, over here, if you'd consider the point that is diametrically opposite to xy, it would be the point of coordinates negative x, negative y. Okay, so over here, if this is theta, then this angle here is in fact equal to it. So let me just remove this one. So now this angle is in fact equal to that angle, and this angle would in fact be pi plus theta. Okay, this one was sorry, that goes all the way to here. So this one was pi minus theta, because what I did is go half a turn then remove theta in order to get to negative xy. While for negative x, negative y, what I did is go by half a turn and then add theta, so that would be pi plus theta. Now, why would this be useful? Because, for example, if I had to find sine of 100 and, I don't know, 210, for example. If you needed to find sine of 210 and you do not have access to a calculator, for example. So we know that 210 would in fact be 180 plus 30 degrees. So according to this, 180 plus 30 degrees, if this is 30 degrees, then this, all of this would be 210. According to these, since over here sine is the y, they have opposite y's. So sine of 100 plus 30 degrees would actually be equal to negative sine of 30 degrees. So if 30 degrees have half, for example, as sine, in that case, you'd know that when you add 180 to 30 degrees leading to sine of 210, that would be the opposite of sine of 30. So that would be, in fact, negative half. So this is why these properties are actually useful. Of course, over here, you would not really be asked to memorize them by heart. You could just always deduce them because of the location of the angle in their corresponding quadrant. So for example here, over here we're looking for pi minus theta. Pi minus theta is in quadrant 2. In quadrant 2, cosine is negative. So cosine of pi minus theta is negative cosine theta. And sine is positive. So sine of pi minus theta is equals to sine theta. So it's a plus because in this quadrant sine is positive, and in this quadrant tan is negative. So tan of pi minus theta is negative tan theta. Please notice here that the pi is not really disappearing anywhere. So because this is the first question I'm asked, Miss, where did the pi disappear? The pi did not disappear. What we're saying here is that theta and pi minus theta, these two different angles have the same sign. This is theta here. Let me just redo circle here. If this is theta, then this is pi minus theta. So what we're saying here is that theta and pi minus theta have the same y, so they have the same sign. So the pi here is not really disappearing anywhere. What we're saying is that theta and pi minus theta have the same sign. However, this is cosine theta. This is cosine of pi minus theta. You notice that it's the same distance, but one of them is positive and the other one is negative. So cosine of pi minus theta is the opposite of cosine theta. Okay, so this is in fact a quick way in order for you to determine the sign. But please do not just think that the pi is disappearing anywhere. Okay, what we're saying is that pi minus theta and theta have the same sign, and pi minus theta and theta have opposite cosines and opposite tans. Similarly, if we were to go to pi plus theta, over here pi plus theta is in quadrant 3. In quadrant 3, x and y are both positive, so sine and cosine are both, x and y are both negative. So sine and cosine are both negative, which leads to tan being positive because tan is their ratio. Again, the pi is not really disappearing anywhere. What we're just saying is that if this is tan, if this is theta, this is pi plus theta. So if this is cosine theta, this would be cosine of pi plus theta. So by symmetry, they have the same distance, but one of them is positive, the other one is negative, and it's the same thing for the y's, for sine. Okay, well over here, negative theta is in fact in quadrant 4. In quadrant 4, cosine is positive and sine is negative, which leads to a negative tan. So cosine of negative theta is positive cosine theta. Sine of negative theta is negative sine theta. Just one last remark before we move to the next example is that here when we explained these identities, we were considering theta to be in the first quadrant, as to be an acute angle. However, whatever theta is, these identities always work. This identity would still work if theta was 150 degrees, for example. If theta is 150 degrees, this is 150 degrees. If you consider negative theta, negative 150, this is negative 150. So you'd notice they still have the same cosine and they have opposite signs. So these identities work for any angle theta. But over here, in order to determine the accurate signs quickly, you'd consider as if theta is acute. Okay, so this is in fact to remember. If it's theta in quadrant 1, quadrant 2 is pi minus theta, quadrant 3 is pi plus theta, and in quadrant 4 it would be negative theta or 2 pi minus theta. It could I could have been to reach an angle here. I could have moved by theta units in the negative sense, or I could have moved by 2 pi a full turn and removing theta from it. Okay, so this rule is very, very important to remember. However, if we move to the next example here, we need to write each of the following trigonometric ratios in terms of the trigonometric ratios of acute angles, which we need to in fact be using these identities here. So we either need to use opposite angles or 180 minus 180 plus. So 180 plus which angle, plus or minus which angles gives me 156. Now we know that 156 is in fact 180 minus 24, right? So according to the identities, we're not going to go back and look at the identities. I'm just going to show you how you can determine if it's positive sine of 24 or negative sine of 24. Again, 180 minus an angle that falls in the second quadrant. Remember that you could tell me that what if you're subtracting an angle that is obtuse. I remind you, I just said that in order to determine the accurate size, you'd consider on this trigonometric circle on scratch that you're removing an acute angle. So 180 minus an acute angle that falls in quadrant 2. I'm looking at sine here. In quadrant 2, sine is positive, so that would be positive sine of 24. Note please that in this question they're not asking you to find what sine of 24 is. They're just asking you to write this trigonometric ratios in terms of a trigonometric ratios of an acute angle. Again, 140. 140 is 180 minus 40 degrees. Right? Again, it's 180 minus, so that falls in quadrant 2, where tan is in quadrant 2, sine is positive, cosine is negative, so their ratio is negative. So tan is negative, so that's tan of 40 degrees. Okay? Well, over here, cosine of 320 degrees. Now, cosine of 320 degrees, now, you'd notice that this 320 is closer to 360 than it is closer to 180. So for that reason, we'd consider this as 360 minus 40 degrees. Now, 360 minus 40 degrees, that's a 360, that's a full turn, minus 40 degrees, that's in quadrant 4. Or you can consider as, since cosine is 2 pi periodic, it has a period of 360 degrees or 2 pi, then that would be the same as cosine of negative 40, which negative 40 falls in quadrant 4, where cosine is positive. So that would be plus cosine of 40 degrees. Okay, so let's just do one in radian. 5 pi over 8. Now, over here, the 180 is pi in radian. So this is pi minus. Pi minus what gives you 5 pi over 8? Remember that with a denominator of 8, pi is 8 pi over pi. So I'd need to remove 3 pi over 8 in order to obtain 5 pi over 8. So over here, pi, again, pi minus angle that's in quadrant 2, where cosine is negative. So it's negative cosine of 3 pi over 8. Now, in this last part, we're going to determine the trigonometric ratios of remarkable angles. Now, the remarkable angles are 0, pi over 2, which is 90, pi, which is 180, 3 pi over 2, 3 pi over 2, which is 270, and then 2 pi that brings me back to the same point as 0. Okay, and then in quadrant 1, the remarkable angles that we have are pi over 6, pi over 4, pi over 3, which we've already seen in a previous lesson as 30 degrees, 45, and 60, while pi over 2 is 90, 180, 270, and 360. So this is the full table of remarkable angles, and we need to determine their trigonometric ratios. Now regarding 0, pi over 2, pi, 3 pi over 2, and 2 pi, now over here, you can just determine their sine and cosine based on the coordinates of the points. You'd notice that 0 and 2 pi are at the point of coordinates 1, 0, and x is the cosine and y is the sine. So this is why sine of 0 is 1 and cosine of 0 is, sine of 0 is 0 and cosine 0 is 1. And similarly, sine of 2 pi is 0 and sine of 2 pi is 1. However, if we look at pi over 2, cosine is 0 and sine is 1. So this is why pi over 2, sine is 1 and cosine is 0. So this table of remarkable angles is really important to remember, especially if you don't have access to a calculator. But again, you don't have to memorize it by heart. All you have to do is just know how to read the coordinates of the special points on the unit circle. Now regarding pi, pi is at the point of coordinates negative 1, 0. So cosine is negative 1 and sine is 0. So cosine of pi is negative 1 and sine of pi is 0. And similarly for 3 pi over 2, cosine is 0 and sine is negative 1. However, regarding their tan, if you know sine and cosine, all you have to do is just divide sine by cosine. So over here, just by taking sine alpha over cosine alpha, 0 over 1 is 0. However, 1 over 0 is undefined. It's infinite. That's a limit. And 0 over negative 1 is 0. Negative 1 over 0 is undefined. And 0 over 1 is also 0. However, let's just move to the angles here that are 30 degrees, 45 degrees, and 60 degrees, which are pi over 6, pi over 4, and pi over 3. Now, in order to remember these trigonometric ratios, all you have to do is just remember how we deduced them in the previous lesson using special triangles. A right isosceles triangle, because it has base angles of 45. Okay, so over here, and regarding pi over 6 and pi over 3, which are 60 and 30. So over here I have 30 degrees and I have a 60 degrees in a semi-equilateral triangle. Okay, so over here all you have to do is just remember these. If this is 1 and this is 1, the hypotenuse would be square root of 2 because of Pythagoras. And then if I had this to be 2 and this to be 1, then this would in fact be square root of 3. Okay, because 4 minus 1 is 3. So according to Pythagoras, this would be square root of 3. So if you notice, sine of 30, that's opposite over hypotenuse. So it's half. While cosine of 30 is square root 3 over 2. Okay, well, as for 60, sine is square root 3 over 2, while cosine is 1 over 2, while tan of 30 is 1 over square root of 3, while tan is 60 squared 3 over 1. With practice, you will learn to actually, you will eventually memorize these. But for the time being, you don't really have to memorize them by heart. All you have to know is just for the special vertices of the circle, all you have to do is just figure out the coordinates for cosine and sine, while the ones in quadrant 1, which are 30, 45, and 60, all you have to do is just remember these special triangles. Okay? So, however, for example, in a previous example, I had to determine sine of 2 pi over 3 in a previous lesson, and I immediately used this to be equals to square root 3 over 2. It's because over here, even though 2 pi over 3 is not a remarkable angle, but we know that 2 pi over 3 is pi minus pi over 3, and that falls in quadrant 2 where sine is positive. So according to the transformation formulas, that would be the same as sine of pi over 3, which is equal to square root of 3 over 2. Similarly, for example, if you had to be looking for cosine of 5 pi over 4, now 5 pi over 4 is not a remarkable angle, but you can use the transformation formulas as remarkable angles to determine it. You'd notice that 5 pi over 4 is pi plus pi over 4. Pi plus pi over 4, that's in quadrant 3. In quadrant 3, cosine is negative. So that's negative cosine of pi over 4, which is negative square root 2 over 2. So this is how the transformation formulas could actually be used in order to determine exact values of some trigonometric ratios if they are not remarkable angles, but they could be deduced from remarkable angles.